once I pour it within 5 minutes, I get this shape. I get this locator shape out here. So it becomes much more easier to me. And when I also do it, I make sure I attach a screw to the center of it, so that when it gets casted, it gets casted along with the screw as a whole structure. So I can take the screw and directly plug into my robot arm, and and which would have always already previously have this finger attached to it. So the gripper can be made in no time. So that was the concept in which we were working, and we found these two materials to be highly helpful for us. The second thing was this Fields metal. Fields metal is like a bismuth alloy, which gets melted down at 50 degrees Celsius, and it also takes the shape wherever we pour. And both these things that I've shown here were used to make the molds, and among which we identified the second one as more important to us, because this takes place at a cold temperature, at a room temperature. Whereas when you take off the field metals, you need to heat it and pour it, and there was a little bit of skill that was involved. But in the second case, it was totally not. So this concept was something that we use, to make the molds, and then fabricate it as a whole piece and attach it to the robot, and then make the pick and place operation done. So this in turn was the biggest breakthrough for us to handle different variants, because the standard products whichever we found in the market was something that was not suitable to handle our kind of variants, and also to go with this concept of using parallel grippers or radial grippers to hold it internally or externally were giving us only minimum results. So because of the nature of the product and because of the nature of the process, wherein the flow is undeterminable, we were only left with an option to get an image, get a replica of the inner profile, and attach it to the robot, and then go about holding it. So eventually we ended up finding these materials, which in turn gave us the expected result. So thus this cold forming, which was once a bigger challenge, how to handle these different variants, how to design the gripper systems which is efficient enough to handle all the variants, is now solved actually. And that's what I've shown here, because we have identified the picking unit, we have identified the gripping unit, and how to go about this. And the next one is the teaching method. The teaching method is like how you make this. I've already told you. The teaching method is like how you make the operator understand to use the robot, and how we picks and does the teaching of various positions, and then runs the program. It's a simple procedure that we do, whenever we take an automation project. So that is with respect to the automation perspective of cold forming automation project, and that's how we finalized these things as the important concept with which we would be able to achieve our global objective. The global objective to handle all variants irrespective of what its internal shape is, irrespective of whether it has the flash or something towards it. And that's it. That's the whole idea. I mean, this idea is the most important thing in terms of giving us the result. But as a project, if you take, there are two stakeholders for it when it comes to automation. One is this automation people, and another one is the process people. But if you take, are there any challenges on the process side which needs to be taken care for automation to function effectively? Yes, there are, and we have identified them also. These and we have identified four changes. We have identified four areas on the process side which would result in frequent stoppage of the automation line. And those four things are the knockout of the press. The knockout is basically a cylinder, hydraulic cylinder. On the top of it, the profile is attached, and this profile is used to push the component out of the die once the component is formed on the die. And this knockout is something that is not retaining its home position. This knockout is something that is not attached to the hydraulic cylinder, whereas it is loosely connected through a spring rod. But this often flies out in most of the cases, so it is not possible to make it retain its position. So that is the biggest challenge here. So that needs to be solved on the process side. And next is um, inconsistency in air ejection, because once a component is formed, the pneumatic air ejection is used to fly the component out of the press so that the robot can load the next component. There is a huge inconsistency in its ejection. Most of the time the manual intervention is needed to take the component out and push it out of the die. So that is something that needs to be addressed. And the third thing is the component gets stick to the die, because forming is sticking called as a biting thing, because we call that, sicking as a biting, and this biting is something that is an inherent property of the forming process. So that also needs to be taken care here. So once these four minor corrections are done on the process side, this automation would run foolproof, and it would ensure us in achieving our global objective, which is, you know to establish the non-stop production for the entire shift period, and would also improve the productivity, and would ensure this automation runs uninterrupted, because once the sticking and the air ejection are, ensured properly, there is no need for a man to supervise a person on the automation setup takes place. So that is the reason why we always say an automation system alone cannot give the result that is expected, whereas certain changes in the process also needs to be incorporated to make the project a real success. So these are those four changes which is needed for this particular project, and that's it. That's what we do here. Once we test our concepts, we take trial runs of it. We test the concepts on the automation side as well as on the process side, and make the whole thing happen. And after that, we define our final objective, say this is what we are going to achieve and within this perspective time and all of the stuff. After that, we get into the project execution, where we will commit a date, we will make those investments happen, and then start fabricating and manufacturing it. We also involve the real team, which is the project execution team and the horizontal deployment team, in making the project happen. And then the shop interference, the customer feedback, and the production, and everything takes place. So this is what, with respect to cold forming automation is, and I hope you've understood how we take a project in case automation, and how we conceptualize it, and how do we estimate the cost of it, and how do we take it into the real-time shop, and how exactly the process takes place. So this is what with respect to the project cold forming automation. Hope you really enjoyed it. I'm sorry that I couldn't share any of the photos here, because I mean, taking cameras or mobile phones are strictly prohibited inside the industry. So I hope you understood the concept. I hope it is really clear over here, and also you understood how we generally conceive a project, and what are the various stages it goes through, and what is the final outcome of it. And thank you. Thanks for patiently listening.